Oxygen is one of the most important properties of the ocean. It may be obvious, but marine organisms depend on it to breathe just like us. However, it is significantly harder for them to acquire it compared to us. Water contains up to 40 times less oxygen by volume compared to air and diffuses at a rate 10,000 times slower. This means even small changes in its concentration can have significant impacts on the environment. In the ocean, where physical processes like wind and currents constantly change local conditions, fluctuations in oxygen concentration can be a big problem. As the world evolves as a result of climate change, how will it impact oxygen concentration in the ocean and the animals sensitive to these changes? The ocean's oxygen levels and distribution are maintained by a complex web of processes that can be summarized into three factors: sea and air exchange, circulation, and biology. Sea and air exchange describes the mixing of wind and waves at the surface, which injects oxygen into the ocean. The oxygen is then transported throughout the ocean interior via circulation. Circulation is the time elapsed since a section of water has been at the surface, also known as the ventilation age. For example, a short ventilation age would be in a shallow bay where water can return to the surface often. As a rule of thumb, the deeper you go, the longer it takes for this turnover to occur. Finally, biology is simply the rate at which oxygen is consumed by marine organisms, also described as the oxygen utilization rate. These three processes work together to continually move oxygen throughout the ocean. However, disruption to the balance of this process creates zones where the oxygen utilization rate is high and a slow circulating system leads to long ventilation ages. These areas become oxygen deficient, turning into oxygen minimum zones, or OMZs. This is the average oxygen concentration of the water column of the Atlantic Ocean. Concentration is measured in cubic centimeters per liter, increasing from left to right on the x-axis. As we descend, the oxygen concentration diminishes quickly until it hits its minimum at 3.4 cubic centimeters per liter at 850 meters deep. The concentration climbs afterwards, eventually stabilizing at 6 cubic centimeters per liter at 2,500 meters. Oceans around the world display similar oxygen concentrations. In general, OMZs exist from 400 meters to 1,200 meters deep, sandwiched between oxygen-rich waters in the shallows from short ventilation ages and deep cold water that carry oxygen at a higher density. Physical properties we described earlier maintain OMZ size. However, these zones can grow beyond their natural boundaries if the system is disrupted by temperature and eutrophication. Climate change is increasing global temperatures at historic speeds, with the summer of 2023 being one of the hottest ever recorded around the planet. The ocean is not being spared from this change either. The United States EPA maintains a record of the average global sea surface temperature change from 1880 to 2020, compared to the average temperature between 1971 and 2000 as denoted by the dotted line. The peaks and valleys along the curve incorporate seasonal cycles and the 2 to 7 year cycle of the El Niño Southern Oscillation, or ENSO, in the Pacific. Better known as El Niño and La Niña, this weather phenomenon can last anywhere from 9 months up to 3 to 4 years. El Niño is the warm phase of the cycle, pulling warm water east across the Pacific towards the west coast of the Americas. La Niña is the opposite, pushing warm water west towards Asia, bringing cold water up from the depths along the west coast of the Americas in a process known as upwelling. From 1939 to 1942, an incredibly strong El Niño brought intense, warm temperatures seen in the strong spike in sea surface temps in that time period. Interestingly, the drop in 1945, according to a paper from Schirmeyer in 2008, is the result of differences in temperature measuring between US and British ships immediately following World War II. Since then, measuring has become more streamlined and detailed, leading to less uncertainty seen in earlier records. This gives us undeniable data demonstrating strong, consistent increases in sea surface temperature since the 70s. On a global scale, nearly every sector of the ocean has seen a significant increase in temperature between 1901 and 2020, as denoted by the crosses in each box. The only exception being the southeast corner of Greenland, which has experienced a general cooling. This cooling is due to the weakening of the Atlantic Meridional Overturning Circulation, or AMOC, because I don't want to have to try to say that again. It transports warm water from the tropics up north near Greenland, where it eventually cools and sinks into the ocean, where it recirculates back south. The problem comes from Greenland's accelerated ice melt, which injects fresh water into this system. Fresh water is more buoyant than salt water, disrupting the current. Rather than the warm water from the equator reaching this exchange to cool and sink, it is pushed away as the ice melt mixes with the deep cold water, decreasing its salinity as it is pulled to the surface, creating this cool region seen on the map. Sea surface temp is used as an indicator for what is happening in the ocean interior. As the heat is turned up, water stratification strengthens. Stratification occurs when warm surface water does not mix with the colder ocean interior below it, creating an invisible barrier where the two do not cross, much like how oil sits on top of water. This is due to their differences in density because of temperature. Natural circulation processes have difficulty overcoming this barrier due to the enhanced warming we've seen in recent years. This disrupts two of our three factors: sea and air exchange and circulation. Thus, pockets of water become oxygen deficient, expanding OMZs. Oxygen utilization in the marine environment is primarily driven by the decomposition of organic material. This organic material originates from algae and plant matter that sinks from the surface as it dies. The decomposition process takes oxygen out of the water, replacing it with carbon dioxide. The problem comes from enhanced nutrient enrichment of water as a result of runoff from farmlands, known as eutrophication. This leads to an overabundance of algae and plants. The decomposition process occurs as normal, but at significantly greater magnitude, sucking oxygen out of the water faster than it can be replenished. As you can guess, this decomposition occurs at the average depth of OMZ formation, only increasing their size. It is estimated the ocean has already lost 2% of its global oxygen carrying capacity as a result of warming and changes in biological consumption, with models predicting up to 7% loss by the year 2100, according to a paper in 2017 authored by Schmidtko, Strama, and Visbeck. These forecasts are troubling as many marine organisms are not adapted to lower oxygen levels. Extended time in OMZs can lead to persistent health problems or death as a result of a lack of oxygen in the body to maintain its balance, known as hypoxia. Shark embryos are one of many animals at risk for hypoxia exposure. A subsection of sharks reproduce using a strategy called oviparity, where they lay eggs near the sea floor. The embryos in the egg feed off a yolk and breathe by ventilating water via tail beats through a slit in their egg sac. They are vulnerable during this time due to their immobility and lack of defenses against predation. Instead, they have developed a behavior called a freeze response to hide in plain sight. This is when an embryo freezes its tail beats, essentially holding its breath to prevent detection from a potential predator. Varela and his research team investigated to see if freeze responses are disrupted by lower oxygen content in their paper titled Impacts of Deoxygenation and Hypoxia on Shark Embryos' Anti-Predator Behavior and Oxidative Stress. Embryos from the small spotted cat shark were used as they are a common oviparous shark that live 150 to 400 meters deep, near OMZ limits. In the study, embryos were divided into 3 tanks with different concentrations of oxygen in the water, known as oxygen saturation, based on conditions that can be found in the ocean. After 6 days under the respective treatments, the embryos were tested for their freeze response based on tail beats after a simulated predator interacted with the egg sac. Responses were then compared to investigate differences based on oxygen content in the water. Based on the results, embryos were severely impacted by hypoxic water conditions. In each test, individuals from the hypoxic tank were worse off than embryos in other treatments, as seen in the graphs from Varela et al. Here, different letters over the standard deviation bars indicate significant differences. Under control conditions, survival was 100%. However, deoxygenated and hypoxic survivability dipped to 87.5% and 56% respectively. Hypoxia significantly increased embryo tail beat rate to 68.4 beats per minute to maintain its oxygen supply. The control group was 45.8 beats per minute, while the deoxygenated treatment was a little higher at 47.7 beats per minute. Freeze response was the most impacted by hypoxia, with the behavior only lasting 1.7 minutes after the predator interaction. This was significantly different from the control treatment at 7.4 minutes and the deoxygenated group at 6.7 minutes. Apart from the survival rate, the control and deoxygenated group were not very different. This may demonstrate a bottleneck early in development for an individual's tolerance for oxygen fluctuation, weeding out less tolerant individuals, leaving stronger embryos that can maintain similar behavior durations compared to the control group. These results are important as they highlight oxygen saturation limits for these sharks, which create a baseline for similar species. Some individuals are more resilient than others, as seen in the survival test, but hypoxic conditions were too extreme for those that survived to maintain an adequate freeze response, increasing the likelihood of predation. Prior studies done on small spotted cat shark and other elasmobranchs have shown similar results. Oxygen minimum zones are growing beyond their natural bounds, suffocating our oceans at an alarming rate. Animals are unable to adapt quickly to this change, forcing them out of their natural habitats. As we continue to experience consequences of climate change, we need to be aware of these issues so that they can be addressed. But unless you can change the temperature of the sea or remove OMZs altogether, it's not possible on an individual level to make an impact. What we can do is hold those in power accountable on climate agreements or push for stronger action in an attempt to slow down these changes. It starts with education and understanding oxygen's role in our oceans.